All right, reaction number 14. I guess you could sit here and spend 2 whole weeks watching these. Happy Monday, everybody. Looks like we're going to do some nuclear physics.
In problem number 2, we're asked to consider the decay from gold to mercury via gamma radiation. In this decay, we observe 3 different gamma rays of different energies, and we speculate that the different energy levels are from the various excited states of the mercury, where we expect the energy of the first 2 excited states to be equal to the total energy of that third state. And so we expect that the energy of these first 2 gamma rays should add up to the energy of the third gamma ray. However, when we naively add those together, that's not exactly what we get.
All right, so lots of things going on here. The first thing I notice whenever there's nuclear decay is I look to see, oh, this 198 becomes 198. So the number of protons and neutrons stays the same. So that's why we're talking about all this gamma stuff. So 3 gammas are emitted when gold goes to mercury. So gold must have, I actually don't know my periodic table well enough. I think that means that some protons are turning into neutrons, let's say. And then we have gamma 1, gamma 2, and gamma 3 all being released. This suggests that there are 2 excited states, E1 and E2. Okay. Yeah, okay. So, right. So they're saying if there's 2 excited states, you can go from 2 to 1, or you can go from 1 to 0, or you can go from 2 to 0. And so that's the 3 different ways that you would get gamma energies back. Very, very cool. And then, yeah, they're saying, okay, well, we'd expect this. So what's fascinating about this problem is there's just a ton of scaffolding, right? So compare and contrast this problem and the same problem where you skip from about here to about here, or just skip, like ended with what is going on. So this scaffolding, I think, is very, very cool. It says, look, there's some nuclear recoil that we need to take into account. But I love the scaffolding. I'd love to know if in the future he starts to pull the scaffolding away. Remember, that's what scaffolding is for, to be pulled away. But anyways, very cool problem.
And we end up with some numbers that don't quite agree. However, we can include.
Wow, look at these. Look at how precise these are. Amazingly precise. And my guess is you have to be that precise to sort of find the stuff that's going on here. That's super cool.
The nuclear recoil in order to resolve this a little bit. The total energy of the actual collision is going to be the energy of the gamma ray plus the kinetic energy of the mercury. And we know that the recoil energy is going.
So I guess that's assuming that the gold was standing still, or maybe you could say this is in the frame of reference of the gold, or maybe let's see. Yeah, they're saying a single gold atom. Yeah, so I guess we don't need the kinetic energy of the gold atom here. Maybe we're just saying that it starts at rest. I'll have to think about that.
Going to be fairly small, and we know that it should be something in the keV range, since that's the energy of the photon. And we know that the mass of of Mercury is much bigger than that, so we can treat the kinetic energy non-relativistically. And so I've said that the.
Okay, so let me just do a quick check here. So the mass of the electron is, what am I thinking? I have 511 in my head. Is that 511 kilo electron volts? Yeah. So the electron, let's see, 10 to the minus 31 times 16. Yeah, okay. And then we're talking about a mercury atom, which has, first of all, 2,000 times an electron times an additional, yeah. So there's tons and tons of rest mass energy there. So this thing, yeah, I thought he made a really interesting point. If the gammas are all around the hundreds of kilo electron volts, we kind of expect the kinetic energy to be that small too. You know, he's hoping that he could just use the classical kinetic energy here. I guess another way to go about it is to finish the problem and go back and say, wait a minute, is that okay? And of course, there's some people who say, why would you ever use classical? Just jump right into the relativistic. The relativistic form of kinetic energy always works. If it ends up being an approximation, good for you. So, but students love this, or 1/2 mv squared, and they get sick and tired of, what is it, mc squared minus, minus m naught c squared, which gets ugly, or gamma mc squared. So I thought that was really, really interesting to say, well, okay, these are small-ish compared to the mass energy of the Mercury, so we can just go ahead and use this. I wonder if he'll circle back around to it.
Kinetic energy is just the momentum squared divided by 2 times the mass. We know that the total momentum carried off in by the Mercury is going to be the same as the momentum carried by the photon, which we can get directly from the Einstein relation here. And
Cool.
altogether, we end up with the total energy is the original gamma ray energy plus this correction factor for the kinetic energy. The mass of Mercury, as stated earlier, is pretty large. It's almost 200,000 keV, so it's going to be pretty small compared to this gamma ray. And indeed, when we do those calculations, we see that for
So, it was great to have this on 2 pages, and he scrolled up, and, people, you're thinking and you're wondering what's happening, and then he scrolled up, and here's everything. We've talked about this before, right? So, showing everything versus like having a sheet of paper slowly revealing this. In a problem like this, for me, frankly, I like it all, but I'll be honest with you, as he's talking, I'm probably not going to be listening super carefully. I'm going to be looking here to say, oh, wait, what's going on? And so I think that, it's always this really interesting issue of how much you should reveal while you're talking.
each of these gamma rays, this correction term is pretty small, so about 6 orders of magnitude smaller than the actual energy.
Really small.
But nonetheless, when we add on those corrections and take the difference, we now see that the difference in the energies is exactly 0, at least up to the uncertainty given to us originally, and therefore the problem.
That was very cool. I need to think about that for a second. So he corrected all of the energies to get the total energies, and then he subtracted the total energies to show that they all added up right. Hang on a second. Total energy for gamma 3. Oh, I see. So what it's saying is that, look, this reaction has a photon going and a particle going like this. And all of their energy together must have come from that energy level spacing. So really, this is the energy level spacing. And it just gets divvied up among a photon and some kinetic energy. So if you're asking the question about, about this is really a comment about, from bottom to top should be the same as bottom to middle to top. That is such a cool problem. Such a cool problem. I loved how he set it up. I love the scaffolding. Let's see if he finishes it up with anything else.
Is resolved.
Yeah, okay, so that's how we ended. All right, everybody. Well, thank you so much for paying attention. What I loved about this one was obviously the scaffolding. I also love that you can tell what I listen to and watch at the end of these. And what the heck that convoy is. What the heck is that? Some sort of movie. Anyways, this was really, really interesting about the scaffolding. In fact, I just want to show that again.
To the total energy of that.
This idea that, hey, they obviously need all of this information to hear. How would your students react if there wasn't this additional scaffolding and just said, what the heck, right? Because there's another interpretation here. There's another interpretation, which is that Mercury has 3 energy levels, 1, 2, and 3, and that each of them is getting populated and finding their way all the way down, right? But instead he's saying there's 3. It's hard to do with my hands here. There's 3, and so you get this energy, or you get this energy, or you get this energy. And so I wonder if I would have ever even noticed that these two add up to almost this. And in fact, if I had added them up, I guess he doesn't write down what the discrepancy is. I would have said, good enough, right? Or I maybe would have said, well, it seems like it's within the, what am I trying to say? The difference, the errors that are there. So really cool. I loved how the technology of this, I liked how he talked about, how to just sort of really pound through it and say, well, okay, we had this kinetic energy. And he did say down here, he said, look at this, look at how massive this is. 198 things, each one being, almost a giga electron volt. And so if we're just going to be talking about kilo electron volts, I guess let me check to see, is that where we ended? Yeah, so these are written in kilos. Wait, is that right? Yeah, these are all written in kilo electron volts. So that's another thing that he did is he made sure to write all of this in kilo electron volts. Um, what is this massive number 184406045? What is that? Oh, okay. That's the mass of Mercury in kilo electron volts per c squared, which is a fascinating way of writing a mass. Yeah. So, oh my God, that's kilo. This is literally like 1.24 electron volts. Wow. This is so small. And yet, now he says, aha, man, this is a super cool problem. All right, you guys, happy Monday. And remember, physics teachers are awesome.